Hello, welcome back to AE 2220 Dynamics. In this video, we are going to continue our discussion on Chapter 2, focusing on Newton's second law, and we're going to go through the first example. Here we are told that a block is pushed along a frictionless surface by a force P at a constant angle of theta. Gravity is included, and we're asked to determine the resulting acceleration and normal force for this system. So we're going to go through and we're going to apply this problem-solving algorithm where we'll deal with the kinematics first, and after the kinematics we will then go through and deal with the kinetics, starting with free body diagrams. So first we're going to define a coordinate system. We're going to use Cartesian coordinates, just right here, Cartesian. We're going to pick our origin and we're going to set it right at the left end of the ground as drawn. We're going to have an I direction in the horizontal and a J direction in the vertical, and then we'll have that counterclockwise rotation is positive. We're then going to do position vectors. For this block, we are going to draw from the origin to the center of mass. For our position vector, we're going to call that R. And in order to define R in a coordinate, we're going to need to add several dimensions. So we're going to start by saying R is equal to, and we already have x at t. X measures the displacement of the block horizontally, but we need to know where we are currently from the given position. Now, what you could have done is you could have defined your origin to be right below the center of mass of the block, and in which case you'd only need to introduce a horizontal dimension to describe the starting or current position as drawn. I put it to the left, so I need to introduce both a vertical and a horizontal scalar dimension. I'm going to say, let me try not to overlap that. So for horizontal direction, I'm going to say that this is just a dimension A, and then from the ground in the vertical direction, we'll say that there's a position H. So then our position vector becomes x plus a in the I direction. So this allows us to describe where it will be at any time. In fact, for position vector, I'm going to go ahead and I'm just going to add on here the function notation r of t. Let me move over that equal sign. So x here is a function t, x of t, and then we'll have plus h in the j direction. From here, we're going to go and compute our velocity and acceleration vectors. We'll start with r dot, and I'll drop function notation here. X is a function of time, so we'll get x dot. A is constant, so we'll get 0 from that. So we get x dot in the I direction plus h is a constant, so we're going to get 0j. We can then go and compute the velocity vector, which we'll write as r double dot. And in this case, we're going to get x double dot in the I direction plus 0j. And that's our acceleration vector. For this type of problem, it's because this is just a rectilinear motion, realistically, we end up with having a relatively simple acceleration vector. I just noticed there's a y that's missing on this free body diagram. So we end up with a relatively simple acceleration vector. This is a kind of problem where you will feel very tempted to just write down what the acceleration vector is. Simply because you can just determine it typically by looking at the problem. But it's very important to just practice this and get used to writing out position vectors and you get used to writing out velocity and acceleration vectors, even if it's a simple system like this, or you feel like you can skip ahead and just write down what the acceleration is, because there are many problems where you won't be able to write down what the acceleration is just due to the complexity of the kinematics. Okay, so we're now going to go and look at our free body diagrams shown here, or not shown here. We're going to go and draw a free body diagram. So now we're moving on to the kinetics. So this is where we deal with kinetics. Starting on from here, we'll deal with kinetics. So we're going to draw our free body diagram. Here's our block. We know that first, we have gravity included, so we have gravitational force pointing down. Move move that just to the center here. So we have gravity pointing down, that is mg. The mass of the block is m, so that's mg. There must be some normal force that is pushing up from the ground onto the block. So we have here our normal force N, and then of course we have that force P, which is acting at an angle theta. This is a force that we're going to need to break up into components, into our I and J components. So right here in P up there, and we're going to deal with this in green. So a horizontal component right here, and then a vertical component pointing down. And we know that this angle right here, this angle is the theta. Let's just double check that. Yep, we can see it's drawn there, and it's provided in the problem. So that angle there is theta. P is now the hypotenuse, so on the vertical we're going to get P sine theta, and on the horizontal we'll get P cosine theta. So we now have gone and broken up all of our forces, and we're ready now to apply Newton's second law. We'll start by let's just write out what Newton's second law is, and this is that the sum of the forces is equal to the mass times the acceleration. And we're going to start with the full vector equation. So we'll start with our forces. In the I direction, we have P cosine theta is the only force in the I direction. Plus, and in the vertical direction, we have N, which is pointing upwards, minus mg, minus P sine theta, that's all in the J direction. It's going to be equal to the mass, and our acceleration vector was x double dot in the I plus 0j. That's our full vector equation. We can now go and split this up into components. In the I direction, we will get that P cosine theta is equal to m x double dot. In the J direction, we will get that N minus mg minus P sine theta is equal to 0. And then from this, we were asked, let's just go back up to the beginning of the problem. We were asked to find the acceleration and the normal force. So we're going to use each of these equations to solve for the acceleration. We're going to use the first equation to solve for acceleration, and then we're going to use the second equation to solve for the normal force. So from here, we're going to simplify. And we're going to find that x double dot, that's our acceleration, is going to be equal to P over m cosine theta. That's our first solution. And then for the normal force, we'll just bring over the mg and the P sine theta onto the other side, and we'll find that the normal force is equal to mg plus P sine theta.